Hi, today's lesson is a continuation on topic 3.1 or thermal concepts. So we're going to talk about heat or thermal energy, okay? In particular, we're going to talk about the concept of internal energy. Internal energy is made up of both the potential energy and the kinetic energy of the molecules inside a substance, okay? The potential energy is primarily the bonds and the forces between individual molecules. The kinetic energy is clearly the motion of the molecules. Okay, and internal energy is basically just the sum of those two. That's the total energy or total heat energy that a substance has. So when we talk about temperature, okay, temperature is only the average kinetic energy of the molecules. Okay, this is a key concept that you need to understand in this unit. Okay, that temperature is the average kinetic energy. Some of the molecules may be going faster, some of them may be going slower, but the temperature is measures the average kinetic energy. Nothing about the potential energy. Okay. The potential energy for solids and liquids are measured by expansion. Okay, remember when I add energy to a substance, it gets hotter. The bonds between the molecules tend to stretch. Okay, and so there's more space between the molecules. So if I look at this square piece of metal with a hole in it, okay, if this is my original, whoops. Here's my original, okay, and the number of molecules doesn't change, but the space between the molecules does. So basically, this side is forced to expand, okay. Different materials will expand at a different rate, but it does get bigger, okay. This is the one that confuses people a little. Okay, the hole in the middle of my square, okay, has the same number of molecules as well, and the space between those molecules has expanded. Okay, so the new hole is going to be larger. A lot of people want to think of it like a donut in the oven. Okay, a donut in the oven works under a different situation. There's air expansion going on inside the donut. In the case of metal, there is no air expansion. It's just the space between the molecules. So the hole gets bigger as a result. Okay, liquids, their volume will increase, but gases have no potential energy, at least the ideal gas model that we're going to be working with. As a result, there's no real expansion for a gas. They may increase their pressure or increase their volume or something, but they're not really any potential energy there. Celsius and Kelvin is something we should be fairly familiar with. Celsius is defined from 0 to 100. It's possible to have negative numbers. But Kelvin is an absolute scale, meaning that 0 degrees corresponds to absolute 0. There are no negative degrees on the Kelvin scale. To convert from Celsius to Kelvin, I subtract 273.15. If you're ever in doubt as to which way, do I add or do I subtract, just remember Celsius, 0 degrees Celsius must correspond to a positive Kelvin. And a lot of times we're going to be looking at just change in temperature. Okay, I changed from 0 degrees Celsius to 5 degrees Celsius. In that case, change of 1 degree Kelvin and is the same as 1 degree Celsius. And that's going to be important, okay? Most of our calculations, if you convert everything to the Kelvin scale, there's no problem. But a lot of the problems are only a change in temperature, in which case the Celsius change in temperature in Celsius is the same as the change in temperature in Kelvin. So be careful about what kind of units you are using in your problem and change them accordingly. Heat and temperature are going to be two slightly different terms that we're going to be using. Okay, heat is thermal energy. It's going to be measured in joules or calories. I can transfer heat from one substance to another. Temperature is a different story. Okay, temperature is measured in Kelvin or Celsius. It measures average kinetic energy, but it's not energy itself. Okay, so and it doesn't really move. It's the energy that moves. Okay, the terms entropy and enthalpy we may run across in this unit. Entropy is a measure of the disorder associated with a system. And it corresponds to the second law of thermodynamics. Is basically how much energy is unavailable to be converted to something else. Okay, enthalpy, on the other hand, is a measure of the total heat content of a system. You can almost think of enthalpy as the internal energy. It's not something I can really measure very well, but I can measure the change in a substance's enthalpy. Okay, either in its expansion or in its temperature or in pressure for gases. And that brings us to the 4 laws of thermodynamics. There's really 3 because the 0th law is kind of trivial. It's the transitive property, and that says if substance A is the same temperature as substance B, that's what it means for objects to be in thermal equilibrium. They have the same temperature. And object B is in thermal equilibrium with object C, then A and C are also going to be in thermal equilibrium. And what that means is that there will be no heat transfer between these two objects, or more specifically, the heat that A gives to B equals the heat that B gives to A, so there's no net change. These are the 3 laws of thermodynamics. We don't really need to know them in great detail, but I go over them anyway. The first law is the conservation of energy law. Delta U is the change in internal energy. Okay, and the change in internal energy of a system is going to be equal to the heat that I add to the system plus the work. Okay, remember, force times distance plus the work that I do on the system. And that's just a conservation of energy statement. The second law gets quoted a lot as, entropy or the randomness of the universe is always increasing, which doesn't really help us too much in the level of physics that we're working with. What you need to understand is that the thermal energy only goes from the higher temperature to the lower temperature. Okay, so heat energy goes from hot to cold, never from cold to hot. And the third law is basically absolute zero, that says entropy approaches zero as temperature approaches absolute zero. So the specific heat equations that we're going to be dealing with, okay, the definition of specific heat is the amount of heat required to raise 1 kilogram of a substance by 1 degree Kelvin or 1 degree Celsius. Okay, for example, the specific heat of water is 4,186 joules. It takes that much energy to raise a kilogram of water by 1 degree, say from 2 degrees Celsius to 3 degrees Celsius. Okay, and to do that, to calculate the amount of heat energy, we use the MCAT formula that I talked about last lecture. Okay, that Q, again, Q represents heat energy, and that's going to equal the mass of the substance, C is the specific heat, and delta T is how much the substance has changed temperature, or T final minus T initial. Okay, so here's some examples of specific heat. Okay, lead, copper, steel. The ones I want you to pay attention to, not that you need to memorize any of these, okay, but I need you to pay attention to ice, water, and steam. Okay, these are all different forms of water, solid, liquid, gas, but they all have different specific heats. Okay, so don't think that, well, it's all water, they'll have the same specific heat. The other thing you need to pay attention to are the units on this column. It's in kilojoules per kilogram Kelvin. Pay attention because a lot of times people forget to convert to joules or to kilograms or whatever. Okay, units are going to be tricky on this unit. So, for example, how much energy is going to be required to raise a 5 kilogram block of ice from minus 20 degrees to 0 degrees? Okay, so here's my formula. I'm going to use Q is equal to MC, MCAT, Okay, my mass is given as 5 kilograms. C is given from before, so it's ice, so it's 2.06 times 10 to the third joules, or 2.06 kilojoules. I'll write it in exponent form. And delta T is going to be final minus 20, final minus initial, or just plus 20. So putting it all together, Q is then equal to 5 times 2.06 times 10 to the third times 20, and I end up with 2.06 times 10 to the fifth joules. Okay, and that's how much energy I need to basically raise the temperature of the ice from minus 20 to 0. I'm not melting the ice just yet. Okay, it's not 0 degrees water. It's still 0 degrees ice. Okay, which brings me to the latent heat equation. Okay, because during the phase change, as that ice is melting from solid to liquid form, okay, remember the phase change graph from last lecture. The temperature doesn't change. It stays at 0. So there's nothing I can use. I'm still adding heat. The ice is melting, yes. Okay, but Q equals MCAT doesn't work. There's no delta T. Okay, so instead I need the Q equals ML formula, okay, where L is the specific latent heat. How much energy do I need to actually break those solid bonds or break those liquid bonds? Okay, so here's some examples, okay. Again, here's water, the heat of fusion and the heat of vaporization. We want the kilojoules, okay. Again, they're in kilojoules per kilogram. And so that's the heat of fusion, specific latent heat of fusion. It takes 333,000 joules to melt 1 kilogram of ice. Not from, doesn't change temperature. It goes from 0 degrees ice to 0 degrees water. Okay, and until it's all melted, it doesn't really change temperature. Same with boiling, okay? It's going to take 2,260 kilojoules to boil a kilogram of water into steam. Okay, so here's another example. I have a 250 kilogram block of ice again. Okay, and it starts at minus 5 degrees Celsius, and I add 100 times 10 to the 6 joules of energy. Okay, and so I need to remember that from a phase change, okay, I have solid, melt, and then water. How much energy? Okay, this is 100 times 10 to the 6 joules. Okay, so I'm going to have to do a Q equals MCAT for the ice. Okay, and then Q is equal to ML for ice to water. And then Q is equal to MCAT for the water. Okay, so I may, depending on the values, I may stop somewhere. Okay, and all of these Q's, when I add them up, has to equal 100 times 10 to the 6. So start with the ice. Okay, I have 250 is my mass. This C for ice is given. It's 2.06 times 10 to the third. And delta T is 0 minus negative 5, because I'm raising it to 0, so it starts melting. And when I plug all that in, let's see, what do I get if I plug all that in? Okay, well, let's not plug that in. Okay, and over here I have 250. The latent heat is given as 333 times 10 to the third. Okay, and that's the heat needed to melt it. And since conservation of mass, I'm still going to have 250 kilograms of water. And my C for water is given as 4.19 times 10 to the third joules. And delta T is what I'm going to find, or T final minus T initial. Okay. And since it all adds up to 100 times 10 to the 6, see if you can figure out what the final temperature is, and we'll talk about that next class. Thank you.